Somewhere in a laboratory, cooled to a temperature colder than deep space itself, a machine no larger than a shipping container is attempting something that sounds almost impossible to say out loud. It is trying to simulate the universe, not a metaphor for the universe, not a rough sketch or a simplified model. An actual, physics-accurate reconstruction of the fundamental forces and particles that make up everything that exists, run on a quantum processor whose logic doesn't follow the rules of ordinary computers at all, but instead exploits the strange, counterintuitive behavior of subatomic particles themselves. Just months ago, that machine succeeded, for the first time in history, at directly simulating a fundamental physical interaction that classical supercomputers simply cannot handle. And now scientists across the world are asking a much bigger, much more dangerous question. If a quantum computer can model the tiniest building blocks of reality, could it eventually be pointed backward in time, used to reconstruct the very first moments of the universe itself, the instant before everything we know came into being? Could it finally answer where we came from? Or is this one of those questions that no machine, however powerful, will ever actually be able to answer? To understand why this question has suddenly become serious enough for major research institutions and technology companies to invest heavily in, you first need to understand what actually makes quantum computing so fundamentally different from the computers that power your phone, your laptop, and every supercomputer currently used to model climate systems, protein folding, or financial markets. Ordinary computers, no matter how powerful, process information using bits, tiny units of data that exist in one of exactly two states at any given moment, a 0 or a 1. Every calculation a classical computer performs, however complex, ultimately breaks down into long sequences of these simple binary choices, executed at extraordinary speed. Quantum computers work on an entirely different principle, built around units called qubits instead of bits. Thanks to a genuinely strange property of quantum mechanics called superposition, a qubit doesn't have to exist as strictly a 0 or strictly a 1. It can exist as a combination of both simultaneously, and when you link multiple qubits together, through another quantum property called entanglement, the computational possibilities don't just add up, they multiply exponentially. This is precisely why quantum computers hold such extraordinary promise for certain categories of problems that remain effectively impossible for classical computers to solve within any reasonable amount of time. Problems that involve modeling systems with an enormous number of interacting variables. Systems like, for instance, the quantum behavior of subatomic particles interacting under the fundamental forces that govern the universe itself. That last point is the key to understanding why quantum computing and cosmology, the scientific study of the universe's origin and structure, have started to intersect so directly. The universe, at its very earliest moments, wasn't a collection of galaxies, stars, and planets the way we picture it today. In the first fractions of a second after the Big Bang, the universe existed as an unimaginably hot, dense state governed almost entirely by quantum mechanics, the same strange physics that quantum computers are specifically built to exploit. Classical computers, built on binary logic, are fundamentally limited in their ability to accurately model genuinely quantum systems, because they have to approximate quantum behavior using classical mathematics, a process that becomes exponentially more difficult and computationally expensive as the system being modeled grows more complex. A quantum computer, by contrast, doesn't need to approximate quantum behavior. It is quantum behavior. This has led a growing number of physicists to argue that quantum computers may eventually become uniquely suited, perhaps even the only tool eventually capable, of accurately simulating the extreme quantum conditions that define the universe's earliest moments, conditions that remain, to this day, some of the least understood aspects of physical reality. This isn't speculative, distant science fiction thinking. Real, published research has already begun moving in exactly this direction. In April of 2026, researchers using Google's quantum processor achieved something described as an essential step forward for the entire field, successfully using a quantum computer to directly simulate a fundamental physical interaction for the first time. Research that was subsequently published in the peer-reviewed scientific journal Nature, one of the most rigorously vetted and respected publications in all of science. This wasn't a simulation approximated through classical computational shortcuts. It was a direct simulation, exploiting the quantum processor's own quantum behavior to model quantum physics natively, a genuinely significant technical achievement that demonstrates quantum computers can now tackle certain categories of fundamental physics problems that remain effectively unsolvable using even the most powerful classical supercomputers currently available anywhere in the world. This achievement builds on top of an entire emerging subfield that researchers have begun calling quantum cosmology, and the work happening within it is considerably more advanced and considerably more specific than most people following mainstream science coverage might realize. At Italy's National Institute for Astrophysics, researchers have been actively developing what they call quantum graph neural networks, a specialized form of artificial intelligence specifically designed to analyze what cosmologists refer to as the large-scale structure of the universe, essentially the vast web-like arrangement of galaxies, galaxy clusters, and the enormous cosmic voids between them that spans the observable universe. This cosmic web isn't randomly distributed. It follows complex, non-uniform patterns shaped by the gravitational influence of dark matter, the mysterious, invisible substance that appears to make up roughly 85% of all matter in the universe, despite the fact that scientists still don't know with any real certainty exactly what dark matter actually is. The Italian research team built a hybrid system combining a standard graph convolutional network, a familiar type of classical artificial intelligence architecture, with what's called a parameterized quantum circuit, a genuinely quantum computational element that processes information using qubits rather than classical bits. This hybrid quantum classical system was trained specifically to classify regions of simulated cosmic structure into dense galaxy clusters versus empty cosmic voids, using data modeled on some of the most detailed cosmological simulations currently available to researchers, an approach that represents a genuinely novel application of quantum computing directly toward understanding how the universe's largest structures actually formed and evolved over billions of years. Separately, and perhaps even more directly relevant to the specific question of the universe's origin, physicists at National Taiwan University conducted what they describe as the first study of quantum cosmology performed on an actual physical quantum computer, rather than through theoretical modeling or classical computer simulation of quantum behavior. Their research specifically focused on solving what's called a constrained Hamiltonian equation derived by mathematically quantizing something called the Friedmann equation. For context, the Friedmann equation is one of the foundational mathematical relationships in modern cosmology, describing precisely how the universe expands over time based on its density, its curvature, and various other fundamental cosmological parameters. It's essentially one of the core mathematical tools cosmologists use to describe and predict the universe's overall expansion and evolution. By quantizing this equation, meaning reformulating it specifically to account for quantum mechanical effects, rather than treating the universe purely as a large-scale classical system, and then solving that quantized version, using an actual physical quantum computer rather than a classical approximation, these researchers took a genuinely meaningful step toward using quantum computing specifically to model the universe's behavior under the extreme quantum conditions that would have dominated its very earliest moments, conditions that classical physics, on its own, struggles to adequately describe or accurately model. It's worth pausing here to explain, in plain terms, exactly why the universe's earliest moments present such a genuinely difficult scientific problem in the first place. Because understanding that difficulty is essential to understanding both the promise and the very real limitations of applying quantum computing to this question. According to the current broadly accepted scientific understanding, the universe began roughly 13.8 billion years ago in an event commonly called the Big Bang, an incomprehensibly rapid expansion from an initial state of extraordinarily high density and temperature. Modern physics can describe the universe's behavior with remarkable precision, starting from an extremely short time after this initial event, but the very earliest moments, particularly the period physicists refer to as the Planck epoch, an interval lasting roughly 10 to the negative 43rd power seconds, an amount of time so small it defies any kind of intuitive human comprehension, remain almost entirely beyond the reach of current physical theory. During this period, physicists believe that all four of the universe's fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have existed as a single unified force, before eventually separating into the distinct forces we observe and measure today. The problem is that fully describing this period requires a theory that successfully merges quantum mechanics, the physics governing extremely small scales, with general relativity, the physics governing gravity and the large-scale structure of spacetime, and physicists have not yet developed a complete, experimentally verified theory that successfully accomplishes this merger. This missing piece is sometimes called the search for a theory of quantum gravity, and it remains, quite genuinely, one of the largest unsolved problems in all of modern physics. This is precisely where the potential value and the very real current limitations of quantum computing intersect most directly. Because quantum computers process information in a way that's fundamentally quantum mechanical in nature, some physicists believe they may eventually offer a uniquely powerful tool for exploring exactly the kind of unified quantum gravitational conditions that define the universe's earliest moments, conditions that classical computers, built on fundamentally non-quantum binary logic, are inherently limited in their ability to accurately model. But it's essential to be clear and honest about where things actually currently stand, rather than overstating the maturity of this research. The quantum cosmology work being conducted right now, including the genuinely significant Google Nature publication and the National Taiwan University research on the quantized Friedmann equation, represents early foundational steps within a still developing field, not a solved problem or a completed theory of quantum gravity. These are proof-of-concept demonstrations showing that quantum computers can, in principle, be used to model certain simplified aspects of cosmological physics, not evidence that quantum computers have already, or will imminently, produce a complete, verified account of exactly what happened in the universe's first fraction of a second. It's worth adding a layer of artificial intelligence into this picture as well, because the phrase quantum AI specifically implies a combination of both quantum computing and artificial intelligence working together, rather than either technology operating entirely on its own. And understanding how these two fields are actually being combined in current research helps clarify exactly what's realistic to expect from this combined approach. Artificial intelligence, particularly machine learning systems trained on massive datasets, has already become an indispensable tool across observational cosmology and astrophysics more broadly, entirely separate from quantum computing specifically. Modern cosmological surveys generate staggering volumes of data, and AI systems have proven remarkably effective at identifying subtle patterns within that data that would be effectively impossible for human researchers to detect manually. A massive new three-dimensional map of the universe, built using observational data from over 47 million individual galaxies, represents exactly the kind of large-scale dataset where AI-assisted analysis has become essential, helping researchers extract meaningful patterns related to the distribution of dark matter and dark energy, the mysterious force believed to be responsible for the universe's accelerating expansion. When quantum computing gets combined with this kind of AI-driven analysis, as demonstrated in the Italian research team's quantum graph neural network approach to modeling the cosmic web, the goal is generally to combine the pattern recognition strengths of modern machine learning with the unique computational capabilities quantum processors offer for modeling genuinely quantum mechanical systems, creating hybrid approaches that leverage the specific strengths of each technology rather than relying on quantum computing alone to solve the entire problem independently. There's a specific, genuinely open scientific mystery that this combined quantum AI approach is increasingly being aimed at, one that has grown considerably more pressing and more publicly discussed over the past several years, what cosmologists call the Hubble tension. This refers to a persistent, unresolved discrepancy between two different methods scientists use to measure exactly how fast the universe is currently expanding. One method relies on measurements of the cosmic microwave background, the faint residual radiation left over from the early universe, essentially a snapshot of what the universe looked like roughly 380,000 years after the Big Bang. The other method relies on more direct local measurements of nearby stars and galaxies. These two independent measurement approaches consistently produce meaningfully different values for the universe's current expansion rate, a discrepancy that has persisted and, if anything, grown more statistically significant as measurement precision has improved over recent years, rather than resolving itself as researchers initially expected it eventually would. This tension matters enormously for understanding the universe's origin, because if our fundamental model of how the universe has expanded since the Big Bang contains some kind of systematic error or missing physical ingredient, that would suggest our current understanding of the universe's earliest history and the physical laws governing its evolution remains meaningfully incomplete in ways researchers haven't yet fully identified or resolved. Some researchers have begun exploring whether combined quantum computing and AI approaches might eventually help model more precise, more physically accurate versions of the early universe's behavior, potentially helping resolve this stubborn discrepancy, though this remains, as of right now, a promising research direction rather than a solved problem with a clear, established answer. Given the genuine promise being described here, it's essential, in the interest of honest, balanced reporting, to directly address the very real skepticism and legitimate scientific limitations surrounding this entire field, because overstating quantum computing's current capabilities would badly misrepresent where the actual science currently stands. Perhaps the most striking counterpoint to the more optimistic framing of quantum AI's cosmological potential comes from research published by mathematicians and physicists at the University of British Columbia's Okanagan campus, who used Gödel's incompleteness theorem, a foundational, well-established result in mathematical logic, to construct a rigorous argument that the universe, in its complete entirety, cannot actually be fully simulated by any computer, quantum or otherwise. Gödel's incompleteness theorem, for context, is a landmark result in 20th century mathematics, demonstrating that within any sufficiently complex, consistent mathematical system, there necessarily exist true statements that cannot be proven using only the rules and axioms of that system itself. Applying this logical framework to the question of simulating reality, these researchers argued that fully and completely modeling the universe would require what they termed non-algorithmic understanding, meaning a form of comprehension that cannot, even in principle, be reduced to a step-by-step computational process, regardless of how powerful or how quantum mechanically sophisticated the computer attempting that simulation might be. This represents a genuinely serious, mathematically grounded challenge to the more sweeping, headline-friendly claims occasionally made about quantum computers eventually being able to fully simulate or completely explain the universe's origin, and it's a perspective that deserves to be taken seriously rather than dismissed, precisely because it emerges from rigorous mathematical logic rather than casual skepticism or a general aversion to new technology. This tension between genuine published progress in using quantum computers to model specific, simplified aspects of early universe physics and equally serious, mathematically grounded arguments suggesting that a complete simulation of the universe's origin may be fundamentally impossible regardless of computational power is precisely the honest, unresolved state of this entire field as of right now. Neither perspective has been definitively proven correct or incorrect. What can be said with genuine confidence is that quantum computing represents a real, actively advancing tool for exploring specific and narrower aspects of the physics governing the universe's earliest moments, aspects that remain genuinely difficult or effectively impossible for classical computers to accurately model, while the broader, more sweeping question of whether any computational system could ever fully and completely explain or reconstruct the entirety of the universe's origin remains a subject of legitimate, ongoing scientific and philosophical debate, one that current evidence does not yet clearly resolve in either direction. It's also worth understanding, in practical terms, exactly how far current quantum computing technology actually is from being capable of the kind of comprehensive cosmological simulation that headlines occasionally imply is right around the corner. Quantum computers, as of 2026, remain a genuinely young, rapidly developing technology, one that continues to face substantial engineering challenges around maintaining what's called quantum coherence, essentially keeping qubits stable enough for long enough to perform useful, reliable calculations before quantum effects called decoherence cause errors to accumulate and disrupt the computation. IBM's own research leadership, speaking at the company's major Think conference this year, made a point of emphasizing that useful quantum computing has genuinely arrived, showcasing real, practical applications developed in partnership with major research institutions, including work with the Cleveland Clinic, Oak Ridge National Laboratory, and specialized quantum performance management firm QCTRL, demonstrating quantum computers already delivering genuinely useful results in areas like materials science simulation, in some cases completing specific calculations thousands of times faster than leading classical computing approaches. This represents real, tangible progress, but the specific applications being showcased and validated right now remain considerably narrower and more specialized than the sweeping, headline-friendly idea of a quantum computer capable of comprehensively simulating the universe's origin from first principles. Current quantum cosmology research, including the genuinely significant work described earlier from Google, the Italian National Institute for Astrophysics, and National Taiwan University, involves modeling specific, carefully simplified aspects of cosmological physics, individual equations, specific structural patterns, particular fundamental interactions, rather than a single, unified, comprehensive simulation encompassing the full complexity of the universe's earliest moments and its subsequent 13.8 billion years of evolution. Understanding this distinction matters enormously for setting realistic expectations about where this research field is actually likely to head over the coming years, rather than the considerably more dramatic timeline that popular science coverage sometimes implies. Most researchers working directly in this specific intersection of quantum computing and cosmology describe their current work in fairly measured incremental terms, emphasizing that they're building foundational tools and methods, validating that certain classes of cosmological problems can indeed be meaningfully approached using quantum computational techniques, rather than claiming they're on the verge of some singular dramatic breakthrough that will definitively explain the universe's origin in the near future. The genuinely exciting aspect of this research, from a scientific standpoint, isn't that it promises an imminent, complete answer to where the universe came from. It's that it represents a legitimately new, genuinely promising computational approach to some of the hardest, most persistent, unsolved problems in modern physics. Problems like the search for a working theory of quantum gravity and the unresolved Hubble tension, areas where classical computational approaches have struggled for decades to make significant additional progress using existing methods and existing computing technology. There's a broader, important theme running through this entire story that's worth drawing out explicitly because it says something meaningful about how genuine scientific progress actually tends to happen. as opposed to how it's often portrayed in more sensationalized coverage. Major scientific breakthroughs rarely arrive as a single, sudden, headline-grabbing moment where one previously unsolved mystery gets definitively and completely resolved all at once. They tend to arrive incrementally, built through years or even decades of careful, methodical research, individual studies that each address a narrower, more specific piece of a much larger puzzle, gradually accumulating into a more complete and more accurate scientific understanding over time. The quantum cosmology research currently underway fits squarely into this more realistic, incremental pattern. Google's April 2026 Nature publication represents a genuinely meaningful technical milestone, successfully demonstrating direct quantum simulation of a fundamental physical interaction for the first time. The Italian National Institute for Astrophysics Quantum Graph Neural Network research represents meaningful progress in applying quantum-enhanced machine learning to understanding the universe's large-scale structure. The National Taiwan University research on the quantized Friedmann equation represents a genuinely significant step toward using physical quantum computers to model the specific mathematical relationships governing cosmic expansion under quantum mechanical conditions. Each of these represents real, published, peer-reviewed scientific progress. But none of them, individually or even collectively, represents a complete, finished answer to the sweeping question of exactly how and why the universe began. Given everything laid out here, how should we actually think about the original question driving this entire piece? Can quantum AI solve the mystery of the universe's origin? The most honest, scientifically grounded answer avoids both of the tempting, oversimplified extremes. It would be inaccurate and misleading to claim that quantum computing and artificial intelligence have already solved this mystery, or that they're clearly, definitively, on the verge of doing so within some near-term, easily specified time frame. The actual state of the science is considerably more modest, though still genuinely significant. Quantum computing represents a real, actively developing, and increasingly validated tool for exploring specific, narrower aspects of the extreme physics that govern the universe's earliest moments. Physics that has historically proven extraordinarily difficult, and in some cases effectively impossible, to accurately model using classical computational approaches alone. Combined with artificial intelligence's already well-established strength in identifying subtle patterns within massive cosmological datasets, quantum computing offers a genuinely promising new set of computational tools for approaching some of the hardest, most persistent unsolved problems in modern physics, including the ongoing search for a complete theory of quantum gravity and the stubborn, unresolved Hubble tension in measuring the universe's expansion rate. At the same time, serious, mathematically rigorous arguments exist, including the Gödel's incompleteness theorem-based research from the University of British Columbia, Okanagan, suggesting that a truly complete, fully comprehensive simulation of the universe's origin may remain fundamentally beyond the reach of any computational system, however powerful or however quantum mechanically sophisticated it eventually becomes. Perhaps the most intellectually honest way to frame where this research currently stands is this. Quantum AI is not, right now, solving the mystery of the universe's origin in any complete, definitive sense. What it is doing, in a genuinely meaningful and scientifically significant way, is providing researchers with powerful new tools capable of exploring specific pieces of that mystery with a level of precision and physical accuracy that simply wasn't achievable using classical computing approaches alone. Whether those incremental, carefully validated pieces of progress will eventually accumulate into something resembling a complete, unified understanding of exactly how and why the universe began, or whether some fundamental aspect of that question will ultimately prove to lie permanently beyond the reach of any computational system, quantum or otherwise, remains, as of right now, one of the most genuinely open, genuinely fascinating questions in all of modern science. Given how young this specific intersection of quantum computing and cosmology still is, with the most significant published results emerging only within the past couple of years, it would be considerably premature to declare with confidence which of these outcomes will eventually prove correct. What can be said with real confidence, based purely on the actual published research currently available, is that something genuinely new and genuinely promising is happening at the intersection of quantum computing, artificial intelligence, and cosmology. A combination of technologies and scientific disciplines that simply didn't exist in any meaningful practical form even a few years ago. Machines built to exploit the strange, counterintuitive rules of quantum mechanics are now being pointed directly at questions about the origin of the universe itself, questions that emerged from those exact same strange, counterintuitive quantum rules operating under the most extreme physical conditions. Imaginable, conditions that existed for the briefest possible fraction of a second, roughly 13.8 billion years ago, at the very beginning of everything. Whether that convergence, quantum machines built by human minds, aimed at understanding the quantum origins of the universe, those same minds emerged from billions of years later, eventually produces a complete, satisfying answer, or instead reveals new, deeper layers of genuine, permanent mystery that no computation will ever fully resolve, is a question that current science, as of right now, simply cannot yet answer with any real certainty. But for the first time in human history, we finally have a computational tool built from the same fundamental physics as the mystery it's being aimed at. And that alone represents something genuinely worth paying close, careful attention to as this research continues to unfold in the years ahead.